Although we just looked at Hess's law in terms of combining reactions, Hess's law is actually most commonly used with enthalpies of formation to calculate the enthalpy for a new reaction. So let's look at how that would work. Here's a possible reaction. We would have 4 molecules of ammonia gas reacting with 5 molecules, or again, this could be in moles, to make 4 molecules of nitric oxide and 6 molecules of water. So this is probably another reaction that would occur potentially in the atmosphere. So the idea of the formation equations is that each one of these formation equations is making 1 mole or 1 molecule of a specific compound. So for example, if we were thinking about ammonia here, the formation equation for this would be, let's say we have nitrogen, which is going to be N2, and we have hydrogen, which is H2. We need 1 nitrogen, so that'll be 1/2 of an N2, and we need 3 hydrogens, so that'll be 3 halves. And we would be making 1 mole of ammonia. And the energy for that, if we look it up in the table, is minus 46.11 kilojoules per mole. And these values are available in the thermodynamic tables that I posted on the Moodle, and there's also a certain number of them in our book. So this tells us that we release 46.11 kilojoules per mole of ammonia that we're making. So let's think about how we can relate this to what we've got right here. So notice that we have ammonia here, but we want to make the ammonia into something else. So that functionally means that we really need to undo this ammonia reaction so that we have some free nitrogen and hydrogen atoms for us to work with. Now, that isn't the way that the formation equation works, but because of Hess's law, because we can take any path, we can imagine this path where we undo the formation equations over here on the left-hand side so that we have all of our free elements in their natural elemental state, and then we're going to use them to do the formation equations for the products. Okay, so we can see that if we are undoing these reactions and we undo the formation equations, that means we're going to change the sign on our formation equation. So that means that each time for these reactants, we're just going to swap the sign. So I'm going to write that as minus the formation equation over here. But we also need to pay attention to our stoichiometric value here. Because we have 4 moles of ammonia, not just 1 mole of ammonia, notice that our formation equation is for 1 mole of ammonia. So we know that energy is extensive. So if we have 4 moles of ammonia, we need to multiply this formation equation by the stoichiometric quantity that we have. So what's that going to look like? Let's try this out. So this reaction enthalpy for the whole combustion reaction is going to be minus 4. The 4 is the stoichiometric quantity, and the minus is because we're undoing the ammonia, of the formation enthalpy for ammonia gas, and then we're going to have minus 5 times the formation enthalpy for oxygen gas. And now we're going to be making the nitric oxide and the water. And so that means we're going to have a positive direction. So we don't need to change the sign there. So we're going to make 4 of these nitric oxides. and we're going to make 6 waters. So we're going to have 6 times the formation enthalpy for the water. Okay, so let's look up those numbers. You can pause the video now and use the thermodynamic tables and look up numbers for these, and then you can double check it with me in a minute. All right, so mathematically, our reaction enthalpy is going to be minus 4 times, we just said that was minus 46, so we still need that minus sign. We're going to have them cancel each other out. So we have to be very, very careful with signs on this work. And then we have minus 5. And here's something that may have surprised you. This formation enthalpy, when you looked for it, it's equal to 0. And this is actually where we define the 0 of our enthalpies. Our formation enthalpy equal to 0 is the 0 point for enthalpy all over the place. So we say that each element in its pure elemental state doesn't require any extra energy to get into its elemental state. So we'll just call that a 0 for the formation enthalpy. So that was 0. And then we have plus 4. And then nitric oxide, the formation enthalpy for that is 90.25 kilojoules per mole. And then for water vapor, not water vapor, it's liquid water here, we've got minus 285.830 kilojoules per mole. So when you add these all up, this is a total of minus 1169.54 kilojoules per mole. And when I look at significant digits, I can see that this is addition-subtraction rules, and I have 2 decimal places as my smallest number of decimal places, so I'm going to keep 2 decimal places in my final answer. Okay, so hopefully this calculation makes reasonable sense, and I just want to reiterate that when we are looking at this reaction of ammonia with oxygen gas to make nitric oxide and water, when we undo this formation enthalpy, we're effectively taking this apart, these 4 ammonias, into 2 nitrogens, and what's that going to be? 6 hydrogens. This has no change. And these are now the raw ingredients that we can at least theoretically use in our heads, right? This isn't exactly what's happening, but this is just what we think of as it happening. So we're going to need 2 nitrogens and 2 oxygens to make our 4 nitric oxides. So that's a formation enthalpy. And then we have 6 H2Os and the last, not H2Os, 6 H2s, and those last 3 O2s are going to go into making the waters. So this is minus 4 times the formation enthalpy for the ammonia. This has no change, so that's minus 5 times 0 because there's no change. This is plus 4 times the formation enthalpy for the nitric oxide, and this is plus 6 times the formation enthalpy for the water. Okay, now just to be clear, you do not actually need to write this extra stuff out every time you do that calculation. This is another kind of Hess's law diagram. There's several different ways we can visualize it. And it's just a justification for why we can do the calculation this way. So if this calculation works just fine for your head, you do not need to fuss around with this diagram. If you like the diagram and it makes good sense in your head to draw it out, you can feel welcome to do that as well. So let's go ahead and try another practice problem just to make sure that we've got it. So there's lots of different reactions that we could do. We don't have access to all of the formation enthalpies, of course, in our table, so I have to pick from the ones that are available. Combustion reactions are pretty reliable ones, though, so we're going to do combustion of propane. So we always know that combustion reactions make carbon dioxide and water. And notice this time we're going to make water vapor instead of liquid water. And they do have different formation enthalpies, so please be really careful. So if you're feeling confident, then pause the video here, look up the values for the formation enthalpies in the thermodynamic tables from the Moodle or in the book, because there are a few values in the book anyway. I think these ones might be in it. And then come back together and we will check our work together. All right, so hopefully you saw that we have 1 mole of C3H8, so we need -1 times the formation enthalpy for C3H8 in its gaseous state, and then -5 times the formation enthalpy of oxygen, which I'm sure you remember is 0 again, and then 3 times the formation enthalpy of carbon dioxide gas, and 4 times the formation enthalpy for water vapor. And you also do not have to write out your reaction like this. You can go straight to the numbers if you prefer. Please always do show your units and show all the steps so that I can follow what you're doing, especially if you accidentally make a mistake or something. So the formation enthalpy for C3H8 was positive 20.42, but we get that negative sign because we're undoing the propane. And then we have -5 times 0. And I know this is kind of a pain to write this all out, and you're like, it's 0. Why do I have to write it in there? So the reason I write it in here is to make sure that when I'm looking back at it later, I don't go, hey, what happened with that term? I can see very clearly that it's 0, and so I don't have to wonder about it later. All right, so now we're making carbon dioxide, and we have 3 moles of it, or 3 molar equivalents. So we've got -393.509 is my formation enthalpy for carbon dioxide gas. And then I have 4 water vapors, which has -241.818 kilojoules per mole. So add this all up, and we get -2168.22 kilojoules per mole. That's quite a lot, but that makes sense. This is a combustion reaction, and we can see this is an exothermic reaction. So as I mentioned before, please be careful about the phases and make sure you choose the right value from the table. Often you will have tables really close together, so it could be easy to get carbon monoxide instead of carbon dioxide. There's about 1 billion nitrogen-oxygen compounds, so just make sure you're super careful when you use those tables. Otherwise, though, the calculations should be pretty straightforward. We subtract our reactants with their stoichiometric quantities, and then we add our products with their stoichiometric quantities, and we're looking at formation equation or formation enthalpies for all of them.